Well, hello there. Looking at solution equilibria. This is going to be part 6, and we're checking out the idea of titration. So here's a picture showing titration, and the simple gist of it is that you have an unknown acid or base. So in this case, we have an unknown acid right here of unknown molarity. And so the pH you can see is real low. And then what we're going to do is we're going to take a known molarity of a base, so that's why it says hydroxide right here, and we're going to drop it in here. And as we drop it in here, eventually what happens is you see the hydroxide and the hydrogen ions will combine to make water, and so your pH will slowly change, and it will change to 7. And so at 7, notice that it changed color, and the reason it changed color is because we put in there an indicator, and an indicator is some kind of molecule that changes color when the pH is different. So we have all different sorts of indicators. Now this is showing what's called a titration curve. And so let's kind of analyze this titration curve for just a second, and I'll kind of show you the parts of it, and so you know how it works. So we start down here at 1, so we've clearly got a strong acid that we're titrating. So a weaker acid probably have a little bit higher pH than this. So, and then also there's some other aspects of this titration curve that immediately show you that it's a strong acid. One of which being it says HCl right here. But what we're doing is we're dropping in NaOH. So we got a strong acid combining with a strong base, right? So so what happens is as you add the base, it goes like this, and as soon as it reaches that point where they're just about the same amount of hydroxide and hydrogen ions in there, there's just a few of each left, it's going to shoot up real quick because there's just not very many in there. And so oftentimes what happens when you're titrating is that you get a color change here, and you sort of swirl it and it goes away, and then the next drop hits it right here at the equivalence point. So you see what the equivalence point is. The equivalence point for a strong acid and strong base is 7. And it's 7 because a strong acid and a strong base are going to make two things. They're going to make, they're going to have two things combining to make water, right? So hydrogen and hydroxide. And so what are these little things right here? So this is an indicator, and this is methyl red. And so the idea with this indicator is it changes into these colors at these pHs. And so we always put these things on kind of a pH scale. And so say if you wanted to know when the pH of your solution was going to reach 5, you'd use this indicator right here, because it would change color at 5. It would change, as it passed 6, it would change yellow. And then this one right here is going to change pink, phenolphthalein, at about 8.5, 9. It's going to start to do that. So that sort of explains the titration curve, and hopefully you can kind of imagine what's happening down here. We have a lot of hydrogen ions. We're dropping in hydroxide, so the pH is going up because we have less hydrogen ions, and then at the point that they're even, we get equivalence point of 7, so that's where there's 0. Let's see, you don't want to draw on that too much. And this is what the apparatus looks like. Okay. So now there's a little bit more to this when it comes to looking at what happens with, let's say, weak acid. So here in this case we had a strong acid with a strong base. That makes sense. So I want to show you sort of the difference between a weak acid and a strong acid. So if I was titrating a weak acid, one of the things I notice right off the bat is it starts off at a higher pH, which makes sense. It's a weak acid. It's not going to completely dissociate. It's going to have its conjugate base in there, kind of going back and forth. So it starts right here. And so during this phase right here, whenever you have a weak acid, remember, and you're adding a strong base, you're creating a buffer. So this is kind of what we'd call the buffer phase right here. So in this particular phase, you have a buffer. And so then notice that it starts to get to the equivalence point about right here. If you remember from the last graph, the equivalence point was about halfway up. See, there it is, halfway up that steep rise. And so that's the same for any titration curve. So if you notice that this equivalence point for this strong acid would be about right there, but the weak acid halfway up its thing is right there. So one of the things that we quickly find out about a weak acid is that its equivalence point is actually greater than 7. So and then right here with the strong base, strong acid, it's going to be equal to 7. And so then the opposite is going to be true if you're titrating a weak base. You're actually going to have something that is less than 7. And so I'll explain that a little bit more in detail. So one of the things that comes up quite a bit when we're talking about acid-base titrations is indicators. So here's a graph of different indicators, and you can see that there's a huge range which spans the entire pH scale. So whatever pH you're looking for, you can find an indicator that you could put in your solution that will turn color at that particular pH. So it makes it kind of nice for having a real visual gauge for determining when your pH is going to change color. And so what you would do is you would maybe do some calculations, figure out where your equivalence point is supposed to be, and then put a pH indicator in there that lines up exactly with your equivalence point. Let's see if I had some more. Let's see, I got it all there. Okay, let's do some kind of calculations here real quick. I'm going to take away that and that. All right, so what about predicting equivalence point? Well, I just kind of showed you some different ideas about predicting equivalence point. You can see from this graph right here the equivalence point of the acid, or you have two different acids, right? You have a weak acid right here. This is the equivalence point, and you have a strong acid, which right here is the equivalence point. Whoops, it should be right at 7. So there it is. So you can see that the titration equivalence point for a weak acid is higher than 7. So let's kind of look at why that is. So anytime you have a weak acid and you add a strong base to it, here's what we know. The equivalence point is going to be, so I'll just put PT, equivalence point is going to be greater than 7, right? So I've got some things written out here, some different sort of things that we could look at. So what about like a sodium hydrogen carbonate with a sodium hydroxide? And what's this? Well, we know that the sodiums are not going to do anything, right? Because those are neutral. But the hydrogen carbonate is a weak acid, and this is a strong base. So what's going to happen is for every single one of these, it's going to take one of these and turn into H2O. Now, oftentimes, where we've looked at before, this actually is the bicarbonate ion, right? So it it acts as a weak base a lot of times, and so this time we're saying it acts as a weak acid, and that might be confusing for you. But the reason it acts as a weak acid is that it's in the presence of a strong base. So so things like this, if it has a hydrogen ion to donate, which it does, but we analyzed this ion before in previous video and learned that it's more likely to be basic than it is acidic, and so that was kind of what we learned previous. But this is kind of a new idea of, in the case of a strong acid, I mean, this is strong acid, so this hydroxide is going to take every single one of these hydrogens. So in that sense, this acts like an acid, right? Let's go ahead and clean that up a little bit. All right, so so then what we're left with then is going to be this CO3 molecule, which is a -2 charge. Well, and what's that potentially going to do? Well, that CO2 or CO3 might want to get back to the bicarbonate ion, remember? This is kind of a weak acid with its conjugate base kind of idea. So it could actually do some of this and create hydroxide plus the bicarbonate ion. So that would be a -1 there. And so then that's why this ends up with a pH at equivalence point. So when every single one of these has been taken, you're still left with these in solution. And so they're going to create some extra hydroxides, right, that haven't had hydrogens to attach to. And so that's why your pH equivalence point ends up greater than 7. So here's another example, a strong acid and a strong base. If we're combining a strong acid and a strong base, for example, let's say perchloric acid and calcium hydroxide. So here we have a dibasic. We're going to need double the amount of this. One thing to keep in mind when you're titrating is know if you have this situation, because it's going to take twice the molarity of perchloric acid to match up with calcium hydroxide. But anyways, what's going to happen? Well, strong base, strong acid, every single one of these hydrogens is going to go here. Every single one of these hydroxides is going to go here, right? And so we're going to just make H2O, okay? So then what about the calcium, and what about the perchloric? Well, these are ions from strong acids and strong bases. They're not going to affect the pH. So at this one, when these ions are floating around solution, they're not going to do anything to the pH. So your equivalence point is going to end up equal to 7. All right, so then we've got one more sort of thing that we're going to look at real quick, is what if we had a weak base and a strong acid? And you can imagine what's going to happen. So what is going to happen? This weak base right here is going to end up taking one of the hydrogens, or the hydrogen from here. This is going to completely dissociate. The chlorine is going to do nothing. But then at equivalence point, when every single one of these hydrogens has attached to one of these, you're still left with these in solution. And NH4 has the potential of going to a water and right, and donating a hydrogen and turning back into that NH3. Okay, so this is actually plus here. So this is a possibility. And so because it's not only a possibility, this is what happens. And so then what's that going to do? Well, it's going to give you some surplus hydrogen ions in there. So if you have a weak base and you titrate with a strong acid, your equivalence point, once again, let's do E point PT, your equivalence point is actually going to be less than 7, because it's going to be somewhat acidic, because this is going to be left in solution after we have equivalence, which means every single one of these has combined with one of these. All right, well, hopefully that helps with the idea of equivalence points and sort of predicting equivalence points in your different scenarios, and also what is a titration curve, and how that works.